My research as a climatologist involves trying to better understand the climate system, as well as its impacts on natural and human systems across the American West. One of the systems I study is fire, and fire has certainly changed substantially across the American West over the last century. After a period of relatively high fire activity in the early 20th century, corresponding with multi-decadal drought, we had a lull in fire activity in the middle portion of the 20th century, and then a dramatic uptick ever since. The past 20 years, burned area has been unlike any other 20-year period we've seen in the past 100 years in the context of current sort of settlement patterns, but it doesn't necessarily mean that this last 20 years is unprecedented, right? Prior to European settlement, there used to be a lot more fire. We didn't have fire suppression, etc. So what's behind this uptick? Well, there's several hypotheses, right? And the answer to that is actually there's lots of things going on. So we know that we've had fire suppression. Fire suppression has really sort of ramped up after the 1910 fire season. And then in 1930, we had a federal mandate to basically put fires out when possible. And it is basically, we know that we can put fires out when we have relatively benign conditions, when we have sort of, wetter fuels, weaker winds, etc. And we're largely unsuccessful. Fires are more challenging to control when we have drier fuels, stronger winds, etc. Okay. As we suppress fires, we basically end up increasing the amount of biomass in the landscape. And biomass is one of the main ingredients you need for a fire, right? You can have hot and dry conditions without actually vegetation. You just have hot, dry conditions in a desert. So that's obviously going to be a key ingredient, and that's going to be a pretty key ingredient, particularly in the lower elevation forest that historically had a very short fire return interval. At the same time, we've also seen some changes in climate that have enabled a pretty dramatic increase in the windows for fire activity, expanding the seasonality of when fires can burn, expanding the geographic area where fires can also occur. That has been brought about through a number of factors, including a sort of a earlier snow off date, warmer and drier summers, right? And longer periods of rain-free conditions in the summertime as well. So collectively, this has led to a substantial uptick in the receptiveness in the landscape to ignite and to carry fire, and for fires to become very, very challenging to control and contain. And this is my sort of fire triangle, where we sort of have weather and climate at the top of the triangle, and I'll make an argument that weather and climate is important, both directly and indirectly, in terms of fire activity. So we'll distinguish this in terms of the direct processes. These are processes that are going to act to basically dry out fuels, right? And basically allow for the fuels to be receptive to ignition, receptive to also spreading over a broad enough geographic area, right? Indirectly, of course, climate very much shapes what actually grows in an individual region in terms of the vegetation type, in terms of the vegetation abundance, in terms of the year-to-year abundance in biomass. That's fuel, and that fuel often is essentially what is going to carry that fire. Okay, ignitions come and go. Obviously, they come as natural sources in terms of lightning, also humans. So this fire environment triangle can exist in the absence of humans, and there is some negative feedbacks in here as well, right? After a fire occurs, you reduce fuels. That negative fire feedback is important. But as we add humans into the mix, things become a bit more challenging. Humans add conditions to the landscape in certain areas. Humans also are modifying sort of the land, right? We're removing fuels from the land. We're basically removing real estate that used to burn and replacing it with agricultural lands. We are suppressing fires in areas, and that's leading to more fuel in certain areas. So humans have a substantial role in modulating this otherwise sort of natural Earth system process. Thinking about the role of humans in changes in fire activity, we think about how humans have actually modified some of these ingredients for fire, right? And this, again, it comes about through starting fires, stopping fires, modifying the land surface, including suppressing fires and leading to an overaccumulation of fuels in certain areas, right? I'll be focusing in on the bottom middle panel, which is basically how climate change through this direct effect has increased fire danger and how that has the potential to influence fire activity in certain areas, but maybe not so much in other areas. So while we have seen increases in fire activity in places like the Western United States, in Canada, in Alaska, in Siberia, it turns out that globally, we've actually seen a decline in fire activity over the past 15 to 20 years. And this is sort of limited here globally in terms of the satellite record. The decline is fairly large, up to 25% by and large. Interestingly enough, though, the decline is predominantly concentrated in some of the most fire-prone environments globally, areas that burn, every few years or so. That being primarily the savannas in northern Africa, as well as some grassland environments as well. So in Australia, here in sort of eastern or sort of Western Asia. And if we look at sort of where fire activity has declined globally, it turns out that it's been predominantly declining in areas that are more grassland, shrubland environments, including cropland regions. So one of the hypotheses behind this decline in burned area here in the northern hemisphere savanna is that we've seen increases in cropland usage, and that has basically removed the landscape from being fire prone. Okay. Systems here, but I'll sort of toggle back to some of the more fuel limited systems as well, because they provide sort of a counterpoint to climate change driving increases in fire activity. Looking across the extent of the Western United States in terms of forested area, which is the inset panel there, we see there is a very strong relationship in terms of what drives interannual variability in burned area extent. And that is a measure of fuel aridity, which effectively is a measure of how dry fuels are during the fire season. Okay, so warm and dry conditions lead to increased fuel aridity. That translates generally into more fire on the landscape, which is very, very logical. And we can see, again, 3/4 of the year-to-year variability explained using a metric like fuel aridity. This doesn't require us to account for the fact that we might have humans acting differently on the landscape, all sorts of other factors that might influence whether fires happen on a year-to-year basis. This is purely climate. It's explaining 3/4 of the year-to-year variability at large scales. Okay. What's also rather apparent here is the dots are color-coded such that data post-2000 is red and data pre-2000 is blue. We can clearly see that the climate has shifted towards much higher fuel aridity over the past 40 years or so, and that is translated or corresponded with a substantial uptick in fire activity. Now, this is not only present across the Western United States. In fact, if we look at how these relationships play out globally, and we limit our sort of analyses to forested environments, we find that by and large, most forested environments globally are quite responsive to year-to-year fluctuations in fire danger or fuel aridity. And this is essentially showing us here that this is quite clear in much of the high latitudes, very, very sensitive. Even places in sort of the tropics, in the Amazon, in Indonesia, again, in Southeast Australia, all these areas, these forested environments respond very strongly to interannual fluctuations in fuel aridity, right? What's kind of interesting, though, is that there are areas of the globe that are fairly unresponsive, right? So where you see these areas here, including the southeastern United States, in equatorial Africa, in parts of Southeast Asia, these are places that are effectively decoupled from climate. Fire activity is effectively decoupled from climate, or burned areas effectively decoupled from climate. So that's really interesting, and that might provide some insight later on in terms of how we sort of think climate may change moving forward. These areas also, some of these areas tend to be also highly sort of, there's a high land use imprint in these areas, and that's one potential reason that they may be decoupled. Furthermore, what we also see is that this strength of this relationship between climate and burned area also is very much influenced by sort of environmental factors. And so in this case here, we're looking at how these correlations actually vary as a function of sort of the tree density on that landscapes. And we see that as we move to higher and higher tree density, we see generally stronger and stronger correlations. The correlations start weakening, though, at lower tree density. And this is getting to this point that as you, even though you may be in a sort of a flammability limited system, as vegetation is reduced, you may begin to sort of weaken that relationship. You begin to sort of decouple fire and climate together. Okay, so a couple of years ago, Park Williams and I did a study where we wanted to get a sort of a zero order estimate of how human-caused climate change has influenced fire activity across the Western United States, specifically forested fire activity in the Western United States. So we developed a counterfactual model, and that model basically used observed variability in climate and asked the question, what if we didn't see climate change? How would fuel aridity over the past 40 years look? And likewise, how would that have influenced, area burned? So we did this by taking a consortium of climate models. We got signals of the projected changes in temperature and humidity, and we ran these counterfactual models such that we had observed fuel aridity and we had a counterfactual fuel aridity, which was basically fuel aridity in the absence of man-made climate change. Okay, we used a very simple model to then sort of backcast this to estimate how much climate change has essentially added to the fire burden across the Western US in terms of data since the mid-1980s. And our estimate is that climate change has effectively doubled the extent of forest area. In a very simple sense, right, we have our sort of data here, and we have a linear model, a log linear model, and we can essentially say, here's how fuel aridity would have looked for individual years in the absence of climate change. Everything gets shifted to the left, and everything gets shifted down per that linear model. So this is a very simple model. It omits several factors, or if you will, it latently includes a lot of other factors, but it assumes that they are constant. One thing that is, of course, apparent is that we know we've had a legacy of 100 years of fire suppression. That's sort of baked into this. We're not able to separate out how much of this is fire suppression versus how much of this is climate change. But what we are able to say is that, again, warmer and drier years tend to promote more fire activity. Climate change has promoted much more of these warmer and drier years. And that would logically allow us to conclude that there has been an influence of climate change on burned area extent. Continuing into today, what we also know is that, again, we see generally low amounts of fire during years with low fuel aridity, right? And I would argue that suppression activities are actually intensifying this sensitivity of fuel aridity to burned area extent. So during these sort of more quiescent fire seasons, fires do occur, they're easier to put out, and we end up actually having less area burned. That promotes more fuel in the landscape. Subsequently, we have more extreme fire seasons, right? More extreme fuel aridity. Fires we're unable to control those fires. There's more fuel in the landscape. We're going to see a larger amount of burned area. So my argument here is that actually the strength of this relationship, or the slope of this relationship, is actually being compounded due to sort of the legacy and then the current continuation of fire suppression activities on the landscape. So I mentioned that these relationships vary geographically, and that's of course important. We would like to be able to sort of take this sort of 60,000 foot view and apply it down to more local scales. And so this is an example here for the Sierra Nevada, where we're looking at a measure of sort of fuel dryness on the x-axis. This is the vapor pressure deficit during March through October, and the burned area. Interannual relationships are quite strong in forested environments of the Sierra Nevada, but they're actually quite weak in non-forested environments. So again, even though within a given ecoregion, you may see very different relationships depending on what type of vegetation you're dealing with. Mind you, these non-forested environments are generally at lower elevations, right? There's going to be a lower density of trees there, maybe more sort of grassland environments where they're not going to be necessarily flammability limited. So looking forward, one thing we also have information on, there's actually pretty mixed information in terms of how climate change is going to influence fire activity regionally, globally. Studies, it's hard to compare between different studies. We can sort of break things down in terms of sort of those ingredients though, right? And so one ingredient that we're pretty clear on has already changed and will continue to change is we're going to see more extreme periods of fire danger, right? Fire weather index here specifically. And this study here looks at basically at when, as rated by, or sort of as judged by when the global mean temperature is going to happen, what change in global mean temperature from the pre-industrial period, are we going to see local fire weather indices emerge from their sort of natural background variability? And the answer is that in some places we've already seen that happen, including much of the Mediterranean, the parts of the Amazon. But what's quite compelling here is that going forward, we see a substantial amount of land emerge once we reach 2 degrees Celsius above pre-industrial. And then once we reach 3 degrees Celsius above pre-industrial, we see basically twice as much area emerge from background variability. So to summarize here, again, there's the direct influence of climate change, that being manifest through fuel aridity, fire danger, that is going to have a role in these fuel-rich environments, and that's going to remain intact so long as fuels remain available. I mentioned that there are negative fire feedbacks, right, such that once a landscape burns, you basically remove some of the fuel from the landscape. That potentially is going to reduce that one ingredient. These negative fire feedbacks can provide a buffer for changing fire activity. That being said, across the Western United States, something like 10 to 15% of the forested land has burned in the last 30 to 40 years. It's going to take a long, long time for us to get to negative fire feedbacks at large scales. At small scales, it certainly can happen. In the fuel-limited environments, there's going to be more of a limited influence of climate change directly, right? These are environments that are already hot and dry. If you make them hot more dry, I don't know what you're going to get too much. At some point, you actually may reduce vegetation because you're limiting vegetation productivity. On the other hand, as we see increases in carbon dioxide, there could be some carbon dioxide fertilization that could promote biomass. Precipitation variability is going to be important as well. If you see more sort of wild swings in precipitation from year to year, that may produce that crop of fine fuels that eventually then burns in subsequent years. And lastly, that human fingerprint. Of course, that's going to be pretty important. We know that at least some of the ingredients for future fire are shaping up towards promoting more fire in the future. Exactly how humans are going to modify that signal is a good question. And I make the argument that fire exclusion policies actually can compound the direct influences of climate change, making the system more sensitive, right? On the other hand, we have great examples globally through where land use modification and also the use of fire naturally to remove vegetation can help actually decouple fire activity from climate drivers.